Hey everybody, yeah, as I said, my name's Matt. I work at Uber, this little startup in San Francisco, maybe you've heard of. And I'm really happy to be here in Australia. It's my first time in your great nation. And in case you're wondering, I've already gotten hanging out with kangaroos out of the way. I've already been trolled by drop bears. So in case I'm pretty sure I got the full cultural experience. So no need to cover any of those bases. But what I want to talk to you about is tell you some stories of how some things have broken at Uber. Like while we were scaling Uber, we didn't always do everything right. And I find that at a lot of conferences like this, you get a lot of people telling a lot of cool stories, and it always sounds so amazing, right? I mean, it's like they got their thing all figured out. They don't have any problems. They've managed to build this amazing technology, and it's like super scalable, and it sounds so awesome, and now it's open source, and you know. And so often I've been in the audience thinking like, man, my stuff is like really bad, right? Like my stuff like hardly works. Like it's weird, like am I just bad at my job? And it turns out that like everybody's stuff is broken. Like everybody's stuff is broken everywhere. It's just like, it's not that exciting to go to a conference and talk about like how broken all your stuff is, but I can assure you our stuff is super broken, and what I want to tell you about is how broken some of it is and some of the things that we learned while trying to sort of grapple with the brokenness. So now that we got that out of the way, we got to tick a few more boxes here. Every presentation has to cover impressive sizes of scalability. So Uber's definitely maybe bigger than you might have realized, especially in terms of number of employees, right? Like check out that engineers number. Like 1,500, it's quite a lot. And when I started at Uber about a year and a half ago, there were 200 people. And so now there are 1,500 people. So that's pretty insane. And so far in the United States, we've through October, we've paid out the equivalent of 4.8 billion Australian dollars to drivers. So it's kind of a thing. It's a serious entity in the world, but still, like a lot of people come back to like, what's with the 5,000 employees and 1,500 engineers? Like, what are you guys doing, right? Like, why do you have all that? And I used to be one of these people who would say that until I got sort of a little more involved in what we were doing, and I realized, man, Uber is much more than just a simple app on your phone. Like, it turns out when we operate in all of these different cities, in all of these different countries, all around the world, we're running the same software. But these places all have different rules. They're all kind of, these individual cities are run like separate businesses. And so we have this large and growing global footprint that all needs to sort of run the same software. And people keep inventing new products and new rules, new regulations that we have to operate with. And so that's sort of like one reason. Like one obvious reason is like, man, we gotta deal with all of this different stuff. And riders and drivers can come and go as they please. There are no like shifts. It's a very dynamic marketplace. That's kind of hard to deal with. But the bigger reason that we need all these people is because there are no free users, right? There's no sort of check in your Uber, right? There's no like you take your phone out of your pocket and like, I'm bored, wonder what's going on. I don't know, let's open up Uber and see what's going on, right? Like no one would do that. Like what instead, like the reason you get this app out of your pocket is because you want to actually go somewhere. And so the requirements of sort of high availability and just the general expectations of people when they get, when they run through our platform are much higher, and much higher than I think a lot of people realize. Like when you're talking about like leaving, maybe somebody's getting stranded if your system doesn't work. Like this is a lot of pressure. And so as a result, but also at the same time, people are spending a lot of money, right? Like every one of these transactions, when that a user's interacting with, like we're moving a lot of money through the platform, and we are users are spending a lot of money, we are making a lot of money, drivers are making a lot of money. So the expectations or the impact of every transaction is very high, and so as a result, we can and sort of do spend a lot of time making subtle adjustments, trying to optimize different flows, different things that seem kind of tiny and inconsequential with these kinds of transactions at this kind of scale. These matter a lot more. So that may or may not have convinced you that we still need 1,500 people, but that's the best I can do. There's a bunch of other fancy projects that you can sort of infer from reading various press releases, but I can't talk about those right now. But anyway, what I realized, also working at Uber though, and sort of reflecting back on my career in software, is that this kind of impact, wow, it's kind of important, the software that I'm writing, it actually matters. I realized this has actually been true for a long time, and it's increasingly true of all software. It's not just Uber and software engineers that have this kind of burden. As society, we're putting more and more control of people's lives behind software, and we need to really up our game as an industry to build more reliable software that works better for people, because it really matters. It changes their lives whether we do a good job or a bad job. So in light of all those things I just said, you can imagine if you're growing a team so quickly that it's very, very hard to sort of meet these requirements. And it's a pretty chaotic place to do good engineering. And we're still sort of expanding the transportation business. India and China are big growth areas. But at the same time, we're also rolling out new products to do, to the sort of beyond personal transportation. Delivering items, delivering food, right? So you can imagine, in spite of all of this growth, it's probably, this is a real challenge, right? And it happened really, really quickly. It happened, just sort of snuck up on everybody that wow, this is actually this major important thing that we have to that we have to get right. So let me take you through a little bit of the history of the sort of technology choices that led us to get here. And there's an interesting thing that I found. Because the company's growing so fast, half of the company has only been here for 6 months. And so if you want to ask around and say hey, why did we do it this way? It's probably nobody knows. And in fact, when I wanted to find out, I asked a lot of questions like this, well, why are we doing it this way? Why does this thing work that way? And no one knows. I had to go trawl through all of the Git repos and ask a few old timers, and they have kind of some conflicting versions of history. They don't even all agree why we did what we did. But as near as I can figure, this is the sort of arc that Uber's technology took. In the earliest of days, the technology did not seem like a problem. It didn't even seem like a thing that the company should do. It just seemed like we should outsource it all. Let's write some mobile apps and we'll have somebody else do the back end, and it's fine, because it probably was fine. There were no customers. There were, on either side of the two-sided market, they were just trying to bootstrap it, and really technology was not the problem. But eventually the business started to take off, and they said, okay, well, we're gonna take this in-house. We're gonna do this engineering ourselves. And so we built a couple of services. One is called Dispatch. It was written in Node.js. Another one is called API. And I feel like this API pattern is a pretty common one. A lot of people end up with a sort of everything is the API, and that's still sort of where we find ourselves. But it's sort of interesting also, if you look at these technology choices that we made at the time and compare them to what we would pick now, and in some cases they're the same, and in other cases maybe they don't apply anymore. But I feel generally, at the time, they were the right choices for the problem Uber was trying to solve. So APIs is where the sort of half of the company is written in Python, and they got this ORM called SQL Alchemy. And ORM is another one of these trade-offs that it's probably a good idea in the early stages, probably accelerated development velocity, but as we'll see over time, it became just this anchor that we were shackled to that. This is now just a really, really sort of not a good choice. Also, over time, the dispatch side doesn't actually need to keep the state forever. So for performance reasons, we swap out Mongo for Redis just to keep this sort of transient state. And then we do sort of an interesting thing, which is we had this thing we called ON, which stands for object node. And ON is kind of like a data access layer. So it's sort of how dispatch talks to API. So the reason we did this is because API breaks a lot, like a whole lot, and largely because of this ORM layer. So this ORM layer inadvertently starts opening lots of connections, and they last a long time, and so transaction boundaries are hard to understand, and the database just sort of gets overloaded like a bunch. And as a result, the dispatch side needs to stay up because dispatch has an interesting property, which is if dispatch is up, people can still use Uber as long as they have an account. Like you can still take trips can progress, the system keeps working. But if the API is down, like, that's bad, right? We don't want it to be down. It impacts the business somewhat, but it's not like a crucial, like, major money-losing emergency. So this ON is in place and actually saves us from a bunch of problems. Then after a while, we start realizing, like, man, we can't jam all of this code into this API. This monolith has got to go. So in 2013, we start adding some different services, and written in Python, and we want to use PostGIS, like we're doing a lot of geospatial work, and the really neat feature in Postgres that we wanted to get access to. And we also had some in-house expertise for Postgres. So we switched the main database over to Postgres. But then we decided that Postgres sucks, and we switched back to MySQL because turns out the ORM problems are even worse in Postgres than they are in MySQL, the ORMs. That's a topic for another time, but yeah, so we decided, like, nah, maybe Postgres wasn't the best thing. We're gonna switch back to MySQL. And then we start coming up against some limits. So every year, the way Uber's business works, New Year's Eve is the busiest night of the year, and those animations I showed you earlier from New Year's Eve. And on New Year's Eve, the traffic is roughly double what it would be on any other peak day. And so for much of the end of every year, engineering doesn't make any further progress on features or whatever. It's all about scaling. It's all just like, will we survive New Year's? And so that's basically what they're doing right now, is like just looking at graphs, projecting forward, making sure that it's going to work through New Year's. And so we figure out that in early 2014, we project our graphs forward, and we're like, uh-oh, it's not going to work. Like we've actually hit the limits of what we can get out of the one MySQL or the one Postgres that are running a few of these things. We realized like this one of something model has got to go. We're going to have to shard these databases. And so we start building our own sort of sharding layer. Like everybody's got a sharding layer. Like we have a sharding layer. This thing called schemaless. It's built on top of MySQL, and it's got to finish before the end of the year because we're not going to make it. Like 2014 would have been a meltdown, New Year's Eve, if we didn't do this. But miraculously, we did do it. So obviously, Uber's still here. You didn't read about it in the news that it went down on New Year's. So we get that and just barely make it through. Meanwhile, we're sort of like, we're reworking the dispatch system. So dispatch had been largely the same for a long time. But there was a sort of a year-long rewrite effort for the new dispatch system. Was still written in Node.js, but it's using some other open source stuff that's on our GitHub, and storing the data in React, which is an interesting choice for reasons I'll get into in a minute. But you can imagine with this sort of rapid pace of technology choice switching and adding people to the team, that you would accumulate a lot of what you might call technical debt. And I think this is a really interesting concept because it's this word, technical debt, that people use a lot, but we don't actually all have the same definition for it. Like people say, oh yeah, technical debt, sure, that's a thing you don't like. It just means like a thing you don't like. That's the universal definition. I mean, there are people that have very articulate, sort of, crisp, useful definitions of this, but I find that among my colleagues and friends in the industry, no one agrees what this actually means. At Uber, it does not mean that we intentionally borrowed against the future because we knew that we were cutting corners in exchange for increased velocity. No, we were just making choices that seemed good at the time and probably were good at the time, but now they're no longer good. So this is particularly true of things like the ORM or various database decisions that when we were small, that was actually fine. It was a very reasonable choice to have done this. It's just that we scaled so quickly, so much so quickly that it now no longer is a good choice. The end result of this, of course, is that it breaks. Like, man, it just breaks a lot. And it's, as I talked about at the beginning, like, whenever it breaks is really, really bad. And so, and the way that these things break too, like, it's sad because we made a lot of very responsible choices. Like, we bought, we use the databases that are tried and true, proven technologies like MySQL and Postgres, not any of these fancy, NoSQL things. And we bought our hardware from a name brand vendor, right? Like we did all these things that should be more reliable, but a weird thing happens, which is eventually we got enough of these things, and all of these things are on their own reliable, but as the number of these items increases, the chances that any one of them might be failing at any time goes up. And so at first, it may not have made sense to engineer a system, spend engineering time on a system that resists failure. If that failure only happens once every couple of years, like, who cares? Like, you probably won't even be using that thing in a couple of years when it fails again, right? But as we get more and more and more of these things, eventually the failure rate goes up to the point where now something's failing like once a week. And so that's awkward for our architecture because we made a lot of trade-offs. We made a lot of trade-offs that assumed we could just get reliability by building a system out of reliable components. And that's sort of not where we find ourselves anymore. And to give you a sense of, just to really sort of shock you all, we're not on the cloud. Like, we're not cloud at all. These are our actual computers, like from our actual data center. Because we can control all of those wires, and we know who the network engineers are who cable them together. And if ever we have a question about some machine can't talk to some other machine, we can just solve the problem. But as you can see, that sort of rack goes off to the horizon. Eventually, we just got so many of those glowing blue LEDs that this just wasn't a trade-off that made sense anymore. So meanwhile, we're building all these reliable components, like computers and databases, and then, we still have to write software that runs on these things, right? And I can't believe I'm going to do this, but I am going to do this. I'm going to put microservices on a slide and put it up on the screen, but we did also do microservices, and so all right, fine. It's like the microservices conference or whatever. But if you imagine the cumulative failure of all of those computers, right? Imagine how this goes up now that we've added more services, right? And we've broken everything out into lots of tiny little pieces, and boy, oh boy, did we break it up into tiny little pieces. So that's 2 years of microservice progression. Now we have 700 services in production. So that's a lot. And of course, we have a dependency graph. Everyone has a dependency graph. It's meant to shock you. Aren't you shocked? I kind of like this graph because, I don't know, I think it's kind of beautiful. It looks like a Hubble Space Telescope or something. I mean, I don't know, it's kind of cool. But really, it's much more beautiful in the same way a jellyfish is beautiful. Good to look at, but not good to sort of reach your hand in there and grab. Just keep your distance from this kind of beauty. So, as you can imagine, we're not the first people to sort of run across this problem, right? Netflix quite famously built their simian army in a Chaos Monkey and that whole suite. And this is really good stuff, right? This is a way of exercising these failure cases to make sure you understand how it's going to behave. And I really want to give a lot of credit to Netflix for talking about this stuff in public, because I feel like a lot of other companies have failure testing, fault injection kind of systems, but no one ever talks about it, right? So as far as I can tell, the only company that ever does this is Netflix, because they don't want to talk about it. But anyway, more people should talk about it. It's good stuff. There's kind of a generalization of this idea that some of the Netflix people are starting to talk about now too, which I really like, which is called chaos engineering. and it has this really nice idea that I feel is really important, which is that they want to build confidence in a system's capability to withstand turbulent conditions in production. I feel like that's actually the reality of all systems, especially like as if people are changing them, releasing them, like regardless of like when a thing actually fails, right? If a bunch of people working on the same stuff, like trying to release regularly, and just the internet is there and random people are doing random things to you over the internet, like this is a turbulent environment. And being able to understand how your system behaves in these turbulent conditions is really, really valuable. So of course, not to be outdone, we built our own system to do failure testing. Most of the service, or many of the services at Uber start with the letter U, and so we have a deployment system called YOW deploy, and so we cutely called our failure tester YOW destroy. So that's fun. And YOW destroy does the stuff you'd imagine it would do. I hope we can open source this someday, because it's pretty cool. But we can't use it. The Netflix stuff was for AWS, and we have our own bare metal deal, right? So, but anyway, we have this thing where you can abuse your processes in all kinds of crazy ways, and it's awesome. It's awesome. Like it does what you'd expect of. It exposes these really sort of bad behaviors when things fail. And so we start doing this, right? We start encouraging teams to get their software failure tested and make sure you can withstand failure testing like through the development process, because we want to do failure testing in production. And I found a really weird thing about this, which is most engineers were super on board with failure testing in dev, but really not so on board with failure testing in prod. Like, they're really worried about, like, I don't know, it's probably not gonna work, right? Like, it's probably gonna leak, like, users are gonna notice. And like, so we should just not do it, right? Like, why would you wanna break stuff for your users? And of course we can have these like really deep, intense conversations where we're like, listen, as an engineering professional, surely you would like to understand the characteristics of your system under turbulent conditions or whatever. And yeah, maybe we eventually see we get to a good place where we realize, like, okay, service authors, sorry, but at least for new stuff that you build, like, we're not going to break your old stuff because we just know it's going to break, right? Like, there's no sense failure testing a thing that like users will notice every single time. Like, we know there's no handling for these things, which is unfortunately a bunch of our software is like that. But at least for new stuff, right? Like, at least for new stuff, let's do failure testing. And so generally speaking, like, people kind of get on board with this. But then we move on to databases, and databases run on computers, and computers fail, so we should do failure testing on databases, right? And I say this, and people look at me like I'm crazy. They're like, you can't failure test the database. Are you insane? Like, databases are reliable. They stay up. This is not a realistic scenario that you're trying to put us through. Like, you don't kill the database randomly. You just gently caress it through its life, and if you ever need to move it somewhere else, like, let's orchestrate an orderly migration. And but yeah, I mean, I think we really do. I think the failure modes of databases are among the worst. And so I really think we need to do failure testing on databases. And so the problem though, like why is it? Like, why don't people want to do failure testing on databases? And so the big reason is because the way these sort of traditional like MySQL and Postgres kind of databases do they get scalability and availability is they have replication. And the replication has like a special node that you can sort of send reads and writes to, and then other nodes downstream of that you can just send reads to. And that means that there is like a special node right at the beginning of it that if that node breaks, then it's really bad, right? So you can maybe failure test the other ones, but please don't failure test the main one, right? And so that's a problem. And another problem, sort of not really a technical problem, but like just as important of a problem, is what do we call these things? Like master and slave. Like, slave is just, it's so gross, right? I mean, like, slavery is a moral abomination, and the legacy is still like felt in countries around the world. And man, oh man, like, just really kind of an offensive term. So I feel like people are really like just married to this term. Like, we should really call it master and slave. Like, it's perfectly acceptable. And oddly, the people who keep wanting to do that are always white men. So that's probably just a coincidence. I don't know. just something I noticed. But you know, the thing is, there are so many better words you could use for this, right? That more accurately sort of reflect what's actually going on. Like you could do leader or follower, right? You could do primary and secondary. And you know, like these are sort of getting at a better metaphor for like what's really going on. But man, you still kind of run into this like this problem of this naming thing, because like in the what you do with a special node, because like what happens if the master dies, right? If the master dies, what you do is you promote a slave, okay? Promote a slave. Like that metaphor does not make any sense. Like no one would ever promote a slave to be a master. It's unheard of. Far better metaphor would be queen and princess, because if the queen dies, how do you get a new queen? Well, obviously the princess, right? Like it's just right there. Other people have suggested to me that maybe this whole, like, because I don't like the metaphor, that maybe like talking about death and that same kind of metaphor is maybe a bad idea, and then I should use much more neutral things, like maybe instead of queen and princess, we should have like US and Canada, Australia and New Zealand. Like, if Australia dies, how do you get a new Australia? You promote a New Zealand to one? Like, I don't know. Anyway, I think there are a lot of good choices here, but the point is that the problem with this is there's a special node at the top. There's this one sort of special node that if you lose, it's going to be really bad. And that property is what has caused our worst outage ever. And I want to tell you about our worst outage ever, not because I want to sort of point out how people made a bunch of mistakes, about how maybe this technology is maybe not the best or has some problems. Like all technology has problems, right? Everything is broken in some way, right? But I think it's really it's a really good way to learn about how these systems fail, kind of in the same way that like aviation disasters are interesting. I mean, they're super gruesome. Like people died, but it's so fascinating as an engineer to be like, whoa, the pitot tubes and the thing, right? Like, so this is an aviation disaster. No one died though, so I think you can maybe you can enjoy it even more thoroughly. So anyway. Where'd my timestamp go? It doesn't matter. So 4 a.m. Oh no, we're going to get to that. So this is the conclusion. This is the actual text from the postmortem. So the internal postmortem. All I did was edit out some of the names of the engineers, and I think I changed all the words slaves to not say that. But anyway, it was down for 12 hours. That's super bad. So 4 in the morning. So Uber has engineering in Europe as well as in the United States, and so we're the database team is making a change, and so we land this patch because we're going to do this China migration, and so we change the way that Postgres updates its write-ahead logs, archive them to S3, so then we can rejigger our replication hierarchy as necessary, and recover from various failures. And so unfortunately, we do it wrong, and now the files are no longer being uploaded. They're just being accumulated on the disk, and that has caused the chart of doom. This is a graph of disk space that's free, and I know it's probably hard to read. At the bottom is 0, that is no disk space, and that little notch there, that is when it hits 0. So I'm not really a database expert, maybe some of you are, but you need more than 0 bytes to run a database. But that's what we had. So obviously this is bad. And but you can see like things were cruising along pretty well, and all of a sudden like, whoa, we're losing our disk space fast. So unfortunately, at the time, the engineer who was on call for this system was dealing with another issue that seemed actually more important. And so he got this page, and it's not like we don't have monitoring, right? Like of course we have monitoring, like we have monitors all over the place. And so this page, like 81 gigs left. And he was like, man, I get that that's a problem, but I got this other thing that's like actually like impacting customers, and plus we have a ton of these Postgres machines. It's probably fine. I'll just have to get to it later. Acknowledge the alert. An hour later, we're like, hey man, you got like 36 gigs. And he's like, I know, but this other thing, it's more important. And so the alert was acknowledged, and then an hour later, 0. Not good. API master database becomes unavailable and the Postgres master crashes. So never fear, because we have a ton of Postgres machines. This is our replication tree, and so the red one is the one that died, where it says DCA1 and Peak1. These are totally other data centers, and inside those data centers, they have a similar replication tree, right? So we have a ton of copies of our data. everything's gonna be fine. We're just gonna get out the runbook and just like sort this thing out, get the site working again. It's no big deal. So engineer notices that the problem is we run out of disk space, and he's just like, man, what's going on with all these WAW files? This is dumb. Why are these all here? Like, I guess Postgres forgot to delete them, which is not the right move. And so we get out the runbook and we're like, okay. We really messed up, but it's no problem. We're gonna promote one of these slaves. Just like I said, you couldn't ever metaphorically do. So we're gonna do it, but we do it wrong because the runbook doesn't quite emphasize or maybe didn't even mention that you had to run this one thing. And so, unfortunately, now we broke a bunch of stuff because now the badness has propagated. And so now we're losing some nodes. We get 8. We think we get 8 going, but it turns out it's not actually going. And we find that out when we try to get some other nodes to follow it. And it turns out that those break too. And so this is bad, right? So we get our consultants on the phone and we're like, hey, please help. The site, it's like super broken, right? We've got all these problems, and you got to help us. So meanwhile, this is like 9 o'clock, and I'm around like kind of in solidarity. I don't really work on a database team. I'm trying to help these guys, and there's nothing I can do. It's 9 o'clock, and so I go home, and I took an Uber home, and I did so because we have the ON, and I already have an account, and so while this like worst outage ever crisis is happening, I still took an Uber home. So that was kind of cool. But still, not to take the pressure off these guys, like they are working really hard to try to get this thing going. And after some more investigation, they realized that somehow in the shuffle, somebody like broke one of these files, like it got corrupted, like somehow, like no one's actually sure how it happened. And helpfully, Postgres has this great error message, invalid magic number, 4 zeros. Like, cool, thanks, Postgres. Like, I'll get right on that. So now things are starting to look grim. Like, remember we started out and we were like, wow, look at all our computers. And now we're like, oof, we better get this figured out before we just completely like corrupt our way into oblivion. So, right, but no problem. We got the consultants are on the case, and they suggest that this is sort of step 1, not so destructive. Turns out to be like really slow and doesn't actually work very well. And so then they come up with this plan, which is at midnight, by the way. So this is 12:30 a.m. And so consultants believe they may be able to write a C program that would allow us to promote Postgres 5. This program would bypass the normal safety mechanisms built into Postgres at midnight. And so what do you think we did? We did it. At 3:20 a.m., the C program allows us to issue commands to Postgres 01. Pretty good. We're still not out of the woods. Like things are still like this whole sort of, rerouting the relationships it's making progress, but it still just keeps breaking in these weird, like subtle ways that are hard to understand. But eventually we start getting some machines kind of back up, and we don't need to go into the details of all this, but bad things keep happening. Like we go, hey, this is working well. Like let's try to get one of our other data centers going again, and like we break that one, and so now that data center's not. Sorry, we can't send any traffic to that data center. And after a while, like we work around, and we're like, okay, well we got one other data center going, and all those machines are okay. We have enough capacity that we can sort of turn the site back on. But that was at 10 in the morning. And then it took another 12 hours for the system to like catch up, right? So this was like super, super bad. But the good news is lots of things that are super bad have a lot to teach us. And so what did we learn from this horrible outage? Well, first thing is we had monitoring, but the alert title obscured this like super valuable piece of information that this was the Postgres primary. Like if it had just said that, like, hey man, I know you think your thing is important, but the Postgres primary is running out of disk space fast, he would have been like, all right, I'll fix it. So that's a super subtle thing. Like no one had ever thought like maybe we should add that to the alert text. And also, threshold alerts, nowhere near as useful in this case as the derivative, right? The rate of change of the disk space would have caught this problem instantly. As soon as the engineer who rolled out that replication change, like minutes after they'd done that, the disk space was just plummeting, right? They would have noticed, like, hey, that's weird. Right after I rolled my thing out, the rate of change of disk space alert went off. So we've since gone and added a ton of derivative alerts, which work way better to detect these kinds of things. Thankfully, we made a lot of copies of our critical data, right? We had all those machines, and that allowed us to just like bumble around and just like break stuff, and and at the end we didn't lose any data, which is pretty great. And boy, we should have been practicing this, right? We should have run through this runbook a few times, but the reason that we didn't is because every time you do it, there's some interruption in service. Like there's some amount of time where users might notice that something is slow or delayed, or they might get, errors might leak or whatever. And so we just never practiced it because we were like, it's too invasive, right? But at a high level, these special nodes, right? It just sucks that there's this one thing that is just so important that you can't ever take it down. And also, why are we exposed to the replication internals? The guts of this fancy database are just sitting on the table, and they're like, hey, just go do your own surgery, it's fine. No reason that we would automate any of this, replication, relationships. It's just weird that you even know about those files, right? The database system should take care of those files. So anyway, the special node problem, that's the big problem. And so we're not the first people to notice that special nodes are problematic. Of course, the Dynamo paper, sort of led the way on this. And I love this phrase from the beginning of the Dynamo paper that says, even the slightest outage has significant financial consequences and impacts customer trust. I feel like that was really sort of seeing into the future of the kind of systems that I think we're all going to be called on to build, as things keep scaling, right? So anyway, Dynamo exists, and it's where we get Cassandra, it's where we get Rioc. And so you might think well, without these special nodes, so in these systems you send a request to multiple nodes, and if one of them happens to not work, the system keeps working, you never notice, right? So we're building some new stuff on Rioc. Would Rioc have saved us from this worst outage ever scenario? And turns out no. So one time the Rioc cluster broke, and it broke in a really weird way, which is that it turns out we had a network problem. And the network problem was subtle, didn't happen very often, but there were latency problems. And Rioc's cleverness, this Dynamo model's feature, is also a bug in that it obscured the fact that there were slowness, that the network was being slow, because two of the nodes responded really quickly, and we just kept right on moving. Unfortunately, we also had a misconfiguration which turned out to be a time bomb, so that as load went on our busiest day ever on this cluster, these things sort of cascaded, and the delays got super bad, and our clients did, unfortunately, exactly the wrong thing. When the database is too slow, they just pushed harder, which made the database slower, which made them push harder, and just after a while, the whole thing just runs out of 500,000 file descriptors or whatever, and sadly, the delay cascades all the way to the front end, and all of China was down for 10 minutes. Super bad. So luckily, we still had the old system was there. We could flip the switch back, and thank goodness we still had that old one there, because it would have been really, really hard if we had to sort of somehow dig our way out of this and fix it. So what did we learn from this? Well, we do failure testing, right? We fail these nodes, and it resists those failures. So that's pretty good. But we should have done delay testing. If we had been doing delay testing on the database and on the clients, we would have seen uh-oh, the clients are misconfigured. They're making the problem worse when the database is too slow. And just in general, this kind of back pressure is super hard. It's just hard to get these things right. And there's sort of no good general case answer for this. This is just a thing we just have to keep reminding ourselves, this stuff is just hard. And on the metrics that come out of a Rioc or a Cassandra, there are tons of metrics in these things, but they're all really, really hard to understand, because you can't just Stack Overflow your way to success. You look at these metrics and you're wonder what that means. Turns out Rioc was telling us something about this delay masking thing. we just didn't understand what that metric meant. And it wasn't on the graphs, there were no alerts on it. We're just like, that's some weird React thing. Turns out, if we had been looking at that, we could have saved ourselves from this problem. So really, I feel like the place that we want to get to with the high level point that I come to from observing these kind of failures is that we want to move to a world that's crash only, where we don't have like graceful shutdown and special nodes and where you're never afraid to just kill something, just take it out of service, just shut it down. Like the freedom to do that is what helps us insulate our users from really actual big failures. But it also allows us to move faster because we're not afraid of like accidentally tripping over some super special node. And what I find is people can sort of get on board with this, but when it comes down to like what it will actually take to implement this, it's not even really a technical problem. It's like a cultural problem that to build systems that can be crash only, it requires people to think differently about how their system should work. One example is retries, right? If you want to resist failure testing and not leak these things out to your users, like you're gonna have to be able to retry your stuff. Like it means all of your requests have to be idempotent, and like that kind of like hurts people's brains, but like it is possible to make all of your requests idempotent, and that's a thing you got to do if you want to sort of live in this world. And another big sort of objection to these kind of big microservice deployments and sort of doing failure testing a lot is man, surely this is gonna like slow everything down, right? Because these systems have this really interesting property that like if you have like a system that generally runs fast, but it has kind of like a slow mode every now and then, like 1% of your requests are slow, if you involve a lot of them, it turns out that your users find the slow case much more quickly. And there's the formula. And oops, if you look at, that's the P99 I showed you there, but if the slow case hits on the P95, like you run into the slow case much more quickly. So, and with 700 services, like you can imagine, this is coming up a lot, and especially if we want to start doing failure testing on them, like whatever can we do? Well, the folks at Google have been talking about this for a little while. There's this great presentation from Jeff Dean you should check out. The basic idea is that we took from this is the thing that they call backup requests with cross-server cancellation. And the way that it works is you send an RPC and you can send it to B1 or B2. You'll get the same answer. And when you send your request to B1, you say, by the way, I also sent it to B2. And then, some milliseconds later, maybe 5, it's some magic number later, you send it to B2 and you say, by the way, I also sent this to B1. And then whoever goes to work on this first, they cancel it from the other one. And so that way, if B1 or B2 experience some random GC pause or you destroy them or whatever, the most that your users end up having to wait is 5 milliseconds because the request will get run somewhere else. And so that's a pretty interesting technique, and it starts to sound a lot like the Dynamo model. Like in the Dynamo model, you send a request to multiple nodes, and if one of them doesn't get back to you, it's no big deal. As long as you hear back from 2 of them, off you go. It's an interesting sort of symmetry there. So that's kind of what we're thinking about, like how we're thinking about like handling these sorts of problems. But like, what about if a whole data center were to fail? So. Or you think data center. I mean, if just think availability zone or whatever. Like how are we going to handle a big chunk of machines all going down at once? And so what we've done is started to think about our distributed system as extending all the way out to our mobile phones, and we involve the driver app in this transaction. And so if you imagine that, partner app in the transaction. So if this partner app is making progress on a trip, right? It's cruising along. It's every few seconds it's sending up its GPS trace and sending it to the primary data center. What we do is in the primary data center we have some cryptographic credentials which we encrypt the state digest, and we periodically send it back down to the phone. And then if we need to fail you over to a different data center, DC2 in this case, the partner app starts trying to make progress on that one, and that data center has never heard of this trip. And so it, of course, has the same credentials, and it says, hey, please send me your state so far. And so we actually use this for more than just failing over between data centers. We use this, even within a data center, just to move traffic around so that we don't have to have replicas. We don't have to replicate the state. These high-res GPS traces to many different places. We sort of move them around by storing a lot of this data like inside the partner app. So that's kind of an interesting technique. But really, at the end of the day, like the biggest problem we have with all these systems, and like the thing that causes the most problems, is of course the people. The most reliable that our system ever gets is Saturday and Sunday, because there's no one changing anything on Saturday and Sunday, right? Like if we could just have a system that was as reliable as it is on Saturday and Sunday, like we wouldn't have any of these crazy problems. And it turns out as you look around, like this is sort of what causes like all big problems, right? Like human error causes all the apocalypse or whatever. But that's the problem, is that as we work with these systems, that's when we break them. It's far more, the impact of these sort of human error style changes is usually much, much larger than some accidental software bug or some kind of weird thing that happens 1 in a million times. It's usually when a human comes along and misconfigures something that everything breaks. And that, I believe, is why we should think about this kind of failure testing as, in crash-only design, as like how we build systems in general, because the people are going to come along and accidentally break it anyway. So I feel like that gets us into a better place where our systems can just be more reliable. And I think if you consider the principles of chaos thing, like I think a lot of people they look at some of these turbulent conditions and they want to try to tame them, right? They want to try to eliminate the chaos. And I feel like that's not actually possible. I think that where we find ourselves is needing to live with this sort of this chaotic system and make a reliable system on top of it. And that is all I have. Thanks a lot.